A while ago, I made all this scary bromine in my parents' garage, and now I've decided that I want to throw some aluminum into it. This is one of my favorite reactions, and the last time that I did it was probably over 6 years ago. Now with a bunch of it in a test tube, I just have to drop in some aluminum foil and wait for it to get started. At the bottom, I'm left with a bunch of dirty aluminum bromide salt and a small ball of aluminum metal. I really wanted this metal ball, and after waiting about 10 minutes, it shouldn't be as hot anymore. Now what I have to do is try and carefully get it out of the tube. To clean it up, I just have to drop it into water, and all of the aluminum bromide almost instantly reacts. After a few minutes, I pulled it out, and I'm left with a nice little metal ball.
This strip of niobium has been soaking quite long enough, so let's get you out of there. Always the rinse. A quick rub down to make sure all the debris is off, and now go a little slower because this is the dangerous part. We don't want to touch any of those steel rings or the bowl because that's how you get a little electric shock. And as fun as that always is, I do have dinner plans tonight. So, once we get all the way to the green, which is the end of the anodizing spectrum, I want to do some low-voltage color. The low-voltage colors don't affect the high-voltage colors, so I'm going for a nice indigo here for contrast. Oh, that's looking marvelous. Let's go and give it a quick rinse again, and then on the towel for a rub, rub, rub. And then here we go, that beautiful rainbow. Perfect.
A while ago, I bought this little tube from Russia, and I think it's finally time to crack it open. Inside of it, besides all the sand, is some nice cesium metal. This is very similar to potassium or sodium, but it's even more reactive. It's kept in this glass ampule to protect it from air, and having it break open could be really dangerous. What's interesting though is what happens if I hold it for about 20 seconds. Just the heat from my hand was enough to melt it, and I now have some slightly golden liquid metal. The melting point of cesium is only about 28.5 C or 83 Fahrenheit. This makes it extremely close, but not quite a liquid at room temperature. If I hold it for another minute or so, I can completely liquefy it. I just have to be really careful though, because dropping it in its liquid form would be an absolute disaster. Today, I've decided to do something which I think kind of looks like magic. To get started, the first thing I'll need is solution A, which contains sulfuric acid and potassium iodate. The next thing I'll need to find is solution B, which has starch, malonic acid, and manganese sulfate. The last is solution C, and this one just has hydrogen peroxide. Now, all I need to do is combine them together in roughly equal amounts. The moment solution C is added, it starts changing colors, and then suddenly, it turns almost black. The really cool part, though, is that it doesn't stay that way. It then somehow goes back to how it was, and the cycle starts all over again. This is known as the Briggs-Rosher reaction, and it's one of the very few oscillating chemical reactions. Okay, so I've decided to do a chemical reaction that, in my opinion, kind of looks like magic. The first thing that I need is a bit of cornstarch, and I'll mix this with some boiling water. A small amount of the cornstarch didn't dissolve, and to clear it up a bit, I'll just pour it through some coffee filters. It took a little while to finish, but when it was eventually done, I added some hydrogen peroxide. I'll mark this one as part B, and the next thing that I have to do is make the part A. To do this, I'll need some pills, and I picked up some vitamin C. I only need 2 of them, and all I have to do is crush them and mix them with water. What I'm doing here is pulling out the vitamin C from the pill and leaving behind a bunch of filler. Like before, I'll dump this into some coffee filters to clean it up a bit. Now that it's done, I'll add an entire bottle of iodine disinfectant. The color of it immediately disappears, and this is because the vitamin C is reacting with the iodine. On top of this, I'll add a bunch of water, and that's it for part A. Now, all I need to do is mix together these 2 solutions. At first, it doesn't seem like anything is happening, and it basically does nothing for over a minute. It takes such a long time that I often think I messed something up, but then it suddenly changes. This is called the iodine clock reaction, and I think it's pretty cool.
I was mowing my lawn and I got to thinking, what can I do with all these clippings? Grass is mostly lignin and cellulose. Lignin is an organic polymer that provides structure to plants, and if I can dissolve it away using some sodium hydroxide, I'll be left with fibers of cellulose, which I should be able to use to make some decent paper. I just need to filter out the cellulose and then blend it smooth. Use a screen to trap the fibers and form the page, and then something heavy to press out the excess moisture. That's science for the win.
For this video, I'm just going to be doing something that I find fun, and all I need is some ammonium dichromate. Now, I just need to pour some into a dish and light it on fire. It's sometimes a bit hard to get started, but it's eventually able to keep going on its own. What's happening here is a decomposition reaction where the ammonium dichromate is chemically falling apart. As it does this, it turns into green chromium oxide, and it produces a bunch of nitrogen gas and water vapor. At some point, it kind of starts looking like a little volcano, and it also lets off a lot of heat. It then keeps going like this until all of the ammonium dichromate has reacted. It eventually finished, and I now have a super puffy pile of chromium oxide, which isn't very useful. What's kind of fun, though, is to take a small amount of it and heat it using a blowtorch. Then, if I drop it into a flask full of ammonia gas, it makes a bunch.
A quick romp around in the acid, always the rinse, and then we'll pop it into the anodizing bath. Sometimes I have to color rings before I weave the final piece. So, bronze, excellent. Blue, excellent. Light blue, excellent. A little bit of yellow, then we'll turn to pink, and then to purple, and then we need to finally get to teal. Oh, I did miss that one on the end. Oh, what a lovely teal. Perfect. You know the drill by now. So first the acid, and then the rinse, and then we're going to hook it right up to get some purples. We have quite a few colours to swim through before we get to purple, though. So let's just keep swimming, swim through the blues, swim through the gold. Come on, gold. Oh, very nice. And then the pinks. Oh, so pinky. Purple. There's my purple. There it is. Oh, that's a good purple. Very nice. So metallic. Take a look at that. Oh, when it dries, it will be even more sparkly and purpley. Perfect.
Polymerization? Yes, please. Start by making a 1% solution of sodium alginate. Takes forever. Gotta heat it up, gotta stir it. There's the chemical formula in parentheses there for all of you that are interested. So here's some of the finished polymer solution. And I've added some red food coloring just so we can see what's actually happening when we do the reaction. To polymerize our sodium alginate, we need calcium ions. In our case, we're gonna use calcium chloride. We use calcium chloride because it's extremely soluble in water. I'm going to grab a sample of the polymer using a big syringe. Get rid of any air bubbles. We'll start by adding small drops to the beaker. Now let's just spray the rest in.
Today, I'm going to be doing something that may or may not destroy my microwave. To do this, all I need is to light a match and cover it with a beaker. Then, I'll punch in 60 seconds and start cooking it. At first, it doesn't look like much is happening, but then it suddenly starts doing something kind of scary. This is all plasma, and it's basically just super hot, ionized gas. It's somewhat similar to fire, but much hotter and way more ionized. The moment the microwave turns off, it all disappears.
Hey everybody, Chem Class Rules here. Today we're going to show you the making of the chemical traffic light. Now for this reaction you really only need 4 ingredients: water and indigo carmine that I just added to the flask there. Indigo carmine is a blue food dye and it's also an acid-base indicator. We'll give that a little swirl to get it nice and mixed up. The next ingredient is sodium hydroxide. Sodium hydroxide is also called lye, and it's in most drain cleaners. We'll give it another swirl here to get it nice and mixed, and it's also going to start to show us a little green color. The next thing we're going to add to our flask is going to be some sugar. It has to be glucose or dextrose or reducing sugar. It can't just be regular table sugar. This creates what's known as a reversible oxidation reduction reaction. When we shake the solution up, we're adding oxygen to it, which oxidizes the indigo carmine from yellow to red to green. And then, as the solution sits, the sugar reduces the indigo carmine from green to red to yellow. That's the reason for the color change. So there we've drawn out the different stages of the molecule for you. And there we have our final solution. Starts out yellow, give it a little shake, incorporates some oxygen, oxidizes that indigo carmine up to red. The sugar reduces it back to yellow. If we give it a little more vigorous shake, we go through red and get to green. And as it sits, the sugar reduces it from green down to red. And then if we let it sit, it will come back to yellow. Here we are pouring it out. You see the yellow in the flask and the green in the large beaker. But once we stop adding oxygen, it goes right back to red and then to yellow. Thanks for watching, guys.
For this video, I'm going to try turning this penny into gold, which is something that I've always wanted to do. The first step is to clean the penny, and all I need is some vinegar and some salt. As it sits there, the oxides are getting slowly removed, and while I wait for that to happen, I'll get something else ready. For this mixture, I'll start with some water, and I need to dissolve some sodium hydroxide drain cleaner. When this is all gone, I just have to dump in some zinc metal and turn on the hot plate, and that's basically it. Now, coming back to the penny, it's looking pretty good, and I'll just quickly wash it off and drop it into the zinc mixture. As it sits there, the penny is slowly getting coated with zinc metal. It's now been about 20 minutes, and it looks like it's been completely covered. What I have now is a completely silver penny, which I think is pretty cool. I still think gold is better though, so I dropped it onto a hot plate and cranked up the heat. As it warms up, it slowly changes color, and eventually, it's completely gold. Unfortunately though, even if it really looks like it isn't real gold. It's actually brass, and it formed because the heat caused the zinc coating to combine with the copper in the penny. Just for fun, I decided to make a whole bunch more, but I have no idea what to do with them.